So in the previous video, we discussed about weight, apparent weight, what happens when you ride in an accelerating elevator, all that stuff. Now in this video, we'll discuss an interesting topic, weightlessness, and then we'll explore normal forces. But before that, we'll see few problems related to weight and apparent weight. So here in this question, we are given that a fish whose mass is 5.2 kg is hanged on a ceiling of an elevator by using a fish scale. Now we need to calculate the apparent weight of the fish if the elevator is at rest. In the B part, it is moving upward with an acceleration of 3.5 meter per second squared. And in the C part, the elevator moves downwards with an acceleration of 2.3 meter per second squared. So first, I'm going to draw the free body diagram. So we're going to assume fish to be a point mass like this. Now the weight force is acting vertically downward, W, the gravity force. Apparent weight, WA, in the upward direction. And this direction we are taking to be positive, Y. Okay. Now initially the acceleration is 0 because the elevator is at rest. So A we have equals to 0. Now we can apply the Newton's second law of motion to calculate the apparent weight. So sigma Fy is equals to mass times Ay, and since acceleration is 0, so this is equals to 0. So net forces acting on the body is 0. Now the upward direction we have taken positive, so Wa minus W. This would be the net forces Fy, and that is equals to 0. And from here the apparent weight Wa will be equals to the actual weight W, which is basically mg. Now from here the apparent weight Wa equals to the mass we have 5.2 kgs times g is 9.81, so that is equals to 51 Newton. So this would be the answer for the A part. Now next in the B part, we have to assume that the elevator is moving upward with an acceleration of 3.5 meter per second squared. So this time this acceleration is 3.5 meter per second squared. So again we can use the Newton's second law. So we have sigma Fy, this is the B part that we are solving, is equals to m times Ay, and Ay we have A, which is equals to 3.5. So and sigma Fy is same, that is Wa minus W, because the net forces on the system is same. Okay, is equals to m times A. Now from here the apparent weight W will be equals to W plus ma. Now W we have mg, so we can replace it like mg is equals to m, we can take it common, g plus A. This is the same equation that we derived in the previous video. Now we can put the values. So Wa will be equals to mass we have 5.2 kgs, g is 9.81, A we are given to be 3.5, and that comes out to be as 69 Newton. So this is the apparent weight for the B part. Now for the C part, we have to take that acceleration is in the downward direction with 2.5 meter per second squared. This time it becomes 2.5 meter per second squared. So basically Ay, this is minus 2.5 meter per second squared. Directly we can use this equation. So Wa, the apparent weight, will be equals to mass we have 5.2, g is 9.81, and this time acceleration is minus 2.5, and that comes out to be as 39 Newton. Therefore we see the elevator is moving upward with some acceleration, then the apparent weight is increased to 69 Newton. Further, when the elevator is moving down with some acceleration, the apparent weight is decreased to 39 Newton. Now I'll be giving one practice question to you. So here we have a person whose weight is 750 Newton on the ground. When the same person rides in an elevator that accelerates, the reading on the scale is different. For example, in case A, the reading is 730 Newton. In case B, the reading is 700 Newton. And the case C, we have the reading to be 770 Newton. Now you need to rank these three cases, A, B, C, in the increasing order of acceleration, that is from most negative acceleration to most positive acceleration. And we have taken this direction to be positive y. Now you have to write the answer in the comment box below. If you have any confusion, you can ask me in the comments. Now we're going to discuss an interesting topic, weightlessness. So here you see people are floating in air and their apparent weight at this instant is 0. Or you can say that people are feeling weightless. But the question arises, how we can achieve this? And the answer lies in the equation that we studied in the previous video. The equation is WA, the apparent weight, is equals to m times g minus a. And this result indicate that a person feels lighter than normal weight when riding in an elevator with downward acceleration a. And if the downward acceleration of the elevator becomes g, then the apparent weight becomes 0 and hence the people feel weightless. And space agencies like NASA use the same concept to train their astronaut. Now let's see how they achieve this. So first, the trainees are sent aloft using an airplane. Now the plane flies downward with an acceleration of 9.81 meter per second squared. And while coming down, trainees feel weightless. And then again the plane pulls up to regain the altitude, and this cycle goes again and again. So this is how they achieve weightlessness. Now we'll be discussing the last topic of this chapter 5, normal forces. And here you see a can is at rest on a surface, and from the Newton's second law we can say that the net forces acting on the can is 0. So let's make a free body diagram. So we're going to consider it to be a point object. The weight or the gravity force acts in the downward direction, and this surface exerts a force in the upward direction. And this force is what we call the normal force. And why this is called as normal force? As it is always perpendicular to the surface. Now from the Newton's second law we can write that sigma Fy, this should be equals to 0. We have taken this direction to be positive y. So N minus W, this is the net forces, this is equals to 0, and from here the normal force comes out to be equals to the weight of an object. Now for this case, normal force is equals to the weight, but this is not always true. Let's see some other examples. So here we have a person who is pulling a suitcase of mass 12 kg, and the force exerted by the person is 45 Newton. This force F is 45 Newton and it acts at an angle 20 degrees above horizontal. Now we need to figure out the normal force on this body. Okay, so first I'm going to make the free body diagram. So we're going to assume it to be a point object like this. Now the gravity force W acts in the downward direction, the normal force N in the upward direction, and the force acting on the object is this F, and that acts at an angle 20 degrees above horizontal. This direction we have taken to be positive x, this is positive y. In the vertical direction there is no motion, so sigma y, the net forces in the vertical direction, it will be equals to 0. Now the net forces in the vertical direction, this is, we have the normal force which is along the positive y, so plus N, weight force in the downward, so minus W. Now this force F will have two components in the horizontal and the vertical direction. This is F cosine theta and this is F sine theta. So in the vertical direction we have plus F sine theta, this is net forces, and this is equals to 0. Now from here the normal force in this would be equals to W minus F sine theta. Now the weight, so weight we have mg, mass is 12 kg and g we have 9.81, so this weight is equals to 118 Newton. Okay, so we can put it here, this is 118 Newton. Force we have 45 Newton, sine theta is 20 degrees. Now from here the normal force N, it comes out to be as 103 Newton, and in vector form we can write that N vector is 103 Newton y cap. Now here we see that the normal force is less than the weight. Now we'll see one more example where the normal force will be greater than the weight of an object. So here in this question we are given that a 4.53 kgs holiday turkey is moved towards the center of a smooth table by two people. Now the person 1 exerts a force F1 whose magnitude we have 35.5 Newton, and the person 2 exerts a force F2 whose magnitude is 39.7 Newton. Now this angle theta we have 21.2 degrees above horizontal, and this is 34.6 degrees below horizontal. Now we need to find normal force on the object. So first I'm going to make the free body diagram. So we're going to assume it to be a point object. Now the weight would be in the downward direction W, normal force in the upward direction N. Now this is force F2, and this angle theta we have 21.2 degrees. Now then this is force F1, and this was F2, and this angle we have 34.6 degrees. Now there is no vertical motion for the object, so sigma Fy, it should be equals to 0. The net forces in the vertical direction is 0. This direction we have positive y, and this is positive x. Now the force F2 will have two components in the x and the y direction, so I'm making it here. This is force F2. Its x component is F2 cosine theta 2. This is F2x, we can write, and in the vertical direction we have F2y. This is equals to F2 sine theta 2. Now the force F1 also have two components, so this is the force F1. Now in the horizontal direction the component is F1x, which is equals to F1 cosine theta 1, and in the vertical direction we have F1y, which is equals to minus Fy sine theta 1. Now we can write that sigma Fy, this would be equals to, first we have normal force which is along the positive y, so N, then W is along the negative y, so minus W, and then this F2y is positive, so plus F2 sine theta 2, and this F1y is negative, so minus Fy sine theta 1, and this should be equals to 0. Now from here the expression for the normal force N, this would be equals to W minus, now this should be 1, this is F1 here, so minus F2 sine theta 2, then plus F1 sine theta 1. Now we have to put the values. Now weight of the object W we have equals to mg. Now mass is 4.53 kg, so weight, this would be equals to 4.53 multiplied with 9.81, which is equals to 44.4 Newton. So we can put it here, weight is 44.4 Newton minus F2. F2 is 39.7, sine theta 2 is 21.2 degrees, then plus F1 is 35.5, sine theta 1 we have 34.6. So on solving we'll get the normal force to be equals to 50.2 Newton. Now here we see that the normal force is greater than the weight force. Thus we can say that the normal force can be greater than, less than, or equals to the weight of object.